Okay, so we've been talking about kinetic molecular theory. Kinetic is motion, and the kinetic molecular theory is just talking about the motion of particles. And we saw that all particles are in motion. Even our solids are vibrating in place. Okay, so how do we measure this motion? Well, we have a thermometer. Our temperature is the average kinetic energy. That's the speed of the molecules. Why is it the average? Well, think about the halls of Maryville High School. I know you haven't seen them in a while, but think about them. There is an average speed going down the halls. That doesn't mean everyone's moving at the same speed. Some people are moving faster, some people are moving slower, but if you could hover above and look, the hallway in general is moving at an average speed. And in a glass of water, our molecules, if it's 70 degrees C, are moving all at that 70-degree speed. Sure, a couple are moving faster and a couple are moving slower, but in general, it's all 70 degrees, okay? Now, this was in your Ed puzzle that you saw, or you're going to see. I'm not sure which order you have decided to do it in, but I did have you watch it first. Heat is the energy, which is the kinetic energy. It's the speed plus the amount. So even though I have a 70-degree cup of water, that's not going to heat up a lake very much. But 70-degree tanker of water might heat up a small pond more than that cup will. So even though they are the same temperature, the tanker has more heat. Okay, so now we need to discuss temperature scales. Normally you've done degrees C, which is Celsius, or Fahrenheit, but those are not directly proportional to kinetic energy. Okay, Kelvin, we had to come up with a Kelvin scale because it is directly proportional. What do I mean by this? Okay, the first thing you need to know is in Celsius, water freeze at 0 degrees C, okay? That means at 0, we have our water frozen. But does that mean that motion has stopped? Well, no, it's just a solid. We can actually go even colder than that. We can have a -5, we could have a -10 degrees C. And if temperature is the measure of kinetic energy or the measure of motion, how could we have negative motion? That would be pretty hard. And when we get into our gas laws, that's going to mess up some of our calculations because our calculations is based on kinetic energy and we can't have negative kinetic energy. In degrees Fahrenheit, water freezes at 32 degrees C. Okay, so here is our freezing, if this is our freezing. And this is 32 degrees Fahrenheit. That's where water freezes. And 0 degrees C for Celsius is where water freezes in Celsius. Both of these can go negative, and we can't have negative motion. Okay, let's compare that to Kelvin. So Kelvin is directly proportional to kinetic energy. That means when we have 0 degrees Kelvin, that means we have no motion. And they came up with this, so where motion ceases to happen, that is 0 Kelvin. Okay, where does water freeze? 273 Kelvin is equal to 0 degrees C. So here is our freezing temperature, but we know in a solid there's still vibrational motion. So if I cool it all the way down, which would be negative in Celsius, I cool it all the way down to 0 Kelvin, we now have no motion. So that's what it means when they say Kelvin's directly proportional to kinetic energy. It's directly proportional to movement. So we're going to talk more about Kelvin when we get into our gases unit, which is our next unit. But the conversion is Celsius plus 273 equals Kelvin. Super easy. You just add 273 to Celsius and it's Kelvin. Today you need to know these vocab words, and we are going to talk about phase change diagrams. And I am going to zoom into this a little bit if I can. Yep. Okay. This is the phase change diagram. Our temperature goes up this way, and we're adding energy. So what I want you to think about is water. Okay? Let's put that in there. Think about water. That makes this make more sense. Okay? And water, if I start at a very low temperature, is a solid. It's ice. Okay? And then, if I keep adding more energy, it will freeze or melt. What temperature does water freeze or melt at? Well, if it's water, this would be 0 degrees C. This is where a phase change happens, right? We're going from a solid to a liquid. This is our phase change. Now, something very important to note and that you'll be quizzed on is what happens to the temperature as we add heat. Well, if I'm a solid and I stay a solid and I add heat, the temperature of that solid will increase until it hits the temperature where a phase change will occur. For water, we're going to freeze or melt. And notice, at that phase change, my temperature remains constant. Here, energy is going in to make these particles move faster. I know this because my temperature is going up. But during a phase change, what's happening is we're overcoming those intermolecular forces. And these are the forces in between particles that hold it together. And once we have enough energy to overcome the forces, they will turn into, for here, this will turn into a liquid, and they'll start moving faster and faster, because here I'm going up in temperature, faster and faster, until the next phase change happens. And here, I'm going to condense or boil. We're going to call this vaporize, because this is vaporization. And what temperature does this happen for water? Well, water boils at 100 degrees C. Here's another phase change, okay? I'm going from a liquid to a gas. And since this is a phase change, all the energy is going into changing it from a liquid to a gas, okay? It's breaking apart those intermolecular forces, or the bonds that hold the particles together. We're not talking about making a compound, but we're talking about attractions that hold these guys together. Okay, so here I'm in the solid phase. Well, what about here? What phases are happening when it melts and freezes? Well, it's not completely a solid and it's not yet totally a liquid, so it's a solid and a liquid. It contains both phases. Think about this. If I put an ice cube on top of your desk, it's melting. It's going from a solid to a liquid. Is there liquid there? Well, yes, there's liquid because it's melting on the table. But there's also still the cube of ice that's melting. So we have a solid and a liquid. So during a phase change, you have both phases existing. The temperature cannot start increasing until it changes over completely to a liquid. Once it changes completely to a liquid, I can increase the temperature until I hit the next phase change. And here I'm going to vaporize. Well, if you have a pot of water boiling on the stove, it's going to vaporize. What phases do I have during this phase change? Well, I have the liquid in the pot and I have the gas, because when you boil, it's turning into gas, right? It's vaporizing. And then once it's completely into the gas phase, then I can increase the temperature again until I hit my next phase of matter, which we're not going to talk about. So, to reiterate, as I add heat, my particles move faster and faster until I hit a temperature where a phase change occurs. For water, it's 0 degrees C. For something else, it would be another temperature, so I could use this to decide what kind of material I have. Like if it's aluminum, it would be a much higher temperature to melt aluminum, right? But here, it has gotten enough energy to start changing into a liquid, So I have my solid and my liquid phase until it's completely liquid right here. And then my temperature can start increasing because these particles, as I add heat, will start moving faster and faster. That's the kinetic energy increasing. And we see that by a rise in temperature. Here I don't have a rise in temperature, so what's happening? When I don't have a change in temperature, it's a phase change. Okay, and it's changing from a liquid to a gas, so I have both phases here until it's completely a gas. And once it's completely a gas and it's not changing phase anymore, my temperature or my kinetic energy can start to increase again. Okay, and this is on your page 114. Okay, so now we need to know how to draw these phase change diagrams. And so the first thing you're going to do when you have a graph, and this is going to help you really understand it, is label the lowest and the highest temperature. And this is going to be on our y-axis. So for this we have 5 degrees C. That's our lowest temperature, and we have 110 degrees C. Okay, now this is water. And so now we need to, number 2, label the temperatures where phase changes happen. And you need to know, like I said before, that 0 degrees is where degrees C is where water freezes and melts, and 0's kind of down here by our 5, so you can just guesstimate that. And 100 is where water boils, and that's up here by 110. So we'll put 100 degrees C right there, degrees C. And now we need to draw staggered flat lines where phase changes occur, because at phase changes, there is no temperature change. During phase changes, our energy is going into weakening those attractions between molecules. So at 0 degrees C, I'm going to freeze and melt, and at 100, I'm going to vaporize or condense. Okay, so now we drew our staggered lines, and then we just connect them, and that's it. Okay, after here that goes up. That's it. So now what do we have here? We have solid, we have a liquid, and we have gas. These are our phases. Below 0, it's a solid. From 0 to 100, it's a liquid, and then it is a gas above 100 degrees. Okay, right here, during our phase change, we have a solid and a liquid. That ice cube's melting. We have the solid ice cube and the liquid. And when we boil, we have a liquid and a gas. We have liquid in our pot. It's going off into vapor. Okay, so going this way, what's happening? I'm melting. Going this way, I'm freezing, because this is where my phase change occurs. Up here, going this way, I'm vaporizing. And going this way, I'm condensing. Okay, so these are those we did not spell that right. Condensing. These are our phases that we've learned about, and as we heat it up, we keep changing phases. Okay, so let's analyze this graph. On the sloping portion, sloping means I'm changing, I've got a slope going here. So on these sloping portions, the temperature or the kinetic energy is increasing. On the level portions, the temperature or the energy, the temperature or the kinetic energy is constant. It's staying the same. Okay, going from a solid to a liquid, I need to move faster as a liquid, so energy is being absorbed. Okay, to melt, energy is So I just want to be clear here. The system is whatever we're talking about, and right now our system is our water or our ice or whatever. So to melt, energy is being added to the system. Okay, we need to add energy so our particles can move faster. And to freeze, energy is being released. Okay, so here we're adding and here we're subtracting or losing. Okay, so when we freeze, we're going slower. That means we're losing energy, and that will be released. Okay? On the next page in your blue book, there's another graph. I want you to pause this video and see if you can draw it and label your phases. After you're done drawing the graph, see if you can answer some of those questions. You won't be able to answer all of them because I've cut out potential energy. Okay, so when you're done, unpause this video and let's go over the answers. Okay, so your graph should look like this. Our flat portions are equal to 0 degrees C, okay, and 100 degrees C. This is where our phase changes occur in water. And we have our freezing, melting, solid, liquid, and you can go through and check this is right. Okay, on the x-axis, which goes this way, we have heat. During the flat portion of the graph, what is happening? Well, it's used to weaken those attractions between the molecules so the molecules get farther apart. And once they're far enough apart, we start a new phase. Okay? The potential energy is increased. You don't have to know this because I'm taking out potential energy, and kinetic energy remains the same. The temperature stays the same. Remember, temperature is a measure of kinetic energy, which is how fast those particles are moving. If there's no temperature change, the speed of those molecules remain the same. Heat transfer on the sloping portion. Well, if temperature is going up, my kinetic energy is going up, which means my particles are moving faster. Okay? So increase in the temperature, therefore the kinetic energy or the speed of those particles are moving faster. There's no phase change during this part of the graph, and so potential energy is basically it's increasing just a tidge, but you don't need to know that. So the last thing we're going to talk about is how is heat transferred? Well, it's transferred through collisions, which means it's about motion, which is kinetic energy, which is temperature. So I have this little drawing. Pretend this is a steel rod. And you know, if you put a candle under one end of the steel rod, over time, that other end will get hot. Okay, so this is our flame or our heat. And these little lines are called woozies. It's a very technical term for how fast they're moving. Just kidding. 3 lines mean they're moving faster. 2 lines, not so much. 1 line barely moving, okay, or vibrating in place. So when I heat up this solid, they're vibrating very quickly and they bump into their neighbor. These are the collisions, which makes the neighbors move. And the neighbors bump into their neighbors and so on and so forth. So when we start up at the beginning, when this portion gets really hot, it starts bumping into these. These guys start moving and they in turn bump into these. Right now, I haven't had the heat on very long, so only this portion is moving very fast, and it's slower towards the end to where it's still cold and it's vibrating in place. If I left this heat on for a long time, these would all be moving at the same temperature and they'd all be moving very fast. That's why we can't grab the end of a piece of metal after it's been in the heat for a while. Okay? So basically, heat moves from hot and it transfers its heat to the cold portion. So heat energy moves from hot to cold. It moves from high energy to low energy. So now you will finish the worksheet that I've attached with this and turn it in. Make sure you understand your notes for your test